Now we have come to the plenary session. The first plenary session will be given by Professor Kae Nemoto from National Institute of Informatics, Japan. And the second talk will be delivered by Professor Kwek Leong Chuan from National University of Singapore. This plenary session will be moderated by Dr. Muhammad Hamzah Fauzi. Let me give a brief introduction to our moderator. Dr. Hamzah Fauzi is a senior researcher and the group leader of the Quantum Devices and Technology Research Group, Research Center for Quantum Physics BRIN. He obtained his doctoral degree from Tohoku University in 2013. His research interest is quantum transport and quantum devices. So ladies and gentlemen, please welcome our moderator, Dr. Muhammad Hamzah Fauzi.
Thank you very much, Dr. Suchi, for the kind introductions. My name is, again, Hamzah Fauzi from Research Center for Quantum Physics, BRIN. So I'm happy to chair the very first sessions this morning. So I would like to welcome our two distinguished plenary speakers this morning, Professor Kae Nemoto and also Professor Kwek from Singapore. Thank you very much for our two distinguished speakers for this morning's sessions. So the first talk will be given by Professor Kae Nemoto with the title of the talk, Can Noisy Intermediate Scale Quantum Processor Be Ever Useful? So before we begin the talk, let me briefly read her biography. Professor Kae Nemoto is a theoretical physicist known for her research on quantum optics to quantum information theory. She is a professor at the National Institute of Informatics and at the Graduate University for Advanced Studies, director of the Global Research Center for Quantum Information Science at the National Institute of Informatics, and co-director of the Japanese-French Laboratory for Informatics. Since April 2022, she leads the Quantum Information Science and Technology Unit at OIST Graduate University in Okinawa, Japan. Professor Nemoto was named as a Fellow of the American Physical Society for pioneering the theory for quantum optical implementations of quantum information processing and communications. Recently, she is awarded with France National Order of Merit for her quality research and educations in the field of quantum information. I hope I read it correctly, Nemoto Sensei. So let's welcome, big applause and warm welcome to our first keynote speaker today, Professor Kae Nemoto, please.
Thank you very much. Let me share my slides first.
Right.
Well, thank you very much for the nice introduction. Recently I moved to OIST where scenery is more. Do you see the whole picture? Or
actually, you are displaying two slides.
Okay, so maybe this way is no.
Yeah. Okay.
Is that
okay.
working or not working?
It's okay now. Yeah. Okay.
It's okay now.
Yeah.
Oh, okay.
It's okay.
So I think the Okinawa scenery is more like in Indonesia. I suppose.
I do agree.
I took this photo from the cafe we have on campus.
Right.
Today, I'd like to talk about applications for NISQ processors and new ways of thinking about physical system we can create and control quantum mechanically. As we all know, we have seen the development of quantum computer, and starting from only 5 qubits at the beginning, if you can see the IBM Q experience several years ago, there are only 5 qubits in there. Now, recently, as about only two weeks ago, we have seen the announcement of 432 33 qubits Osprey processor from IBM. So that growth is really remarkable. And now we can say we can control a quantum system, a large quantum system, meaning it has many components, quantum coherently. So that is very important for also the technology, but again, there's a physics and science itself. So we want to see how these things will scale, and eventually it's probably as the technology will achieve fault-tolerant quantum computation. But on the way to this, we will have much more things, not just only one type of application, which is fault-tolerant quantum computer. Of course, fault-tolerant quantum computer is a remarkable achievement if we have created, but at the same time, we never had this kind of large, complex quantum system controlled, and we can see a new type of quantum physics will come out of this kind of systems. So let's think about this system from applications. Although the first remarkable achievement was a 54 qubits device from Google. And at that time, we thought, some people, there are some arguments still, but some people thought we achieved quantum advantage. And in some sense, so we had a quantum advantage in the physical sense, but the computational sense is that really achievement was kind of still questionable. And recently, that's again, so several years later, we have seen that a new algorithm to actually simulate this what that device is doing, and in that sense, we have finding it's very difficult to actually say the quantum advantage we have got with some particular application. That's also true, I think. And one then, of course, we could overcome this to increasing the number of qubits, like we can see in IBM Q development and error mitigation technology and things like this probably reduce the error we will have, or we can evaluate more precisely, and it might some problems we can have quantum advantages, but that is one direction. Today, I want to talk about different ways to think about advantages. So here, one problem we have is if we have using quantum computers or this system as a quantum computer, then we have to decompose physical process, which is a time evolution of the system as a gate sequence. And the gate sequence is problematic because, we have some certain unitary operator we want to apply, and we have to decompose in the gate. And it will take more time than just applying some Hamiltonian development. So in some sense, it's become very interesting because it's working as quantum computer, but at the same time, we lose advantage using natural system with some control. So one way of thinking about it is if we have very limited number of qubits, how we can facilitate that to do something interesting, and how simple system can be useful to do that kind of thing. So that is one thing. And there are, of course, lots of algorithms we have seen. It's most famous probably is variation quantum algorithm. And that's particularly people were interested because it's a combination with quantum part and classical part. And we may be able to facilitate this kind of processor to do something interesting. But so it's turning out after lots of effort, we have a bit of problem. One is that this feature space need to be to generate a complex system. That means unitary needs to be quite complex. That means we need a certain depth to realize that's feature space. So the depth means the time, so that is a little bit problem. And another problem is this classical part. We need to optimize to do the learning, but this tends to get this plateau problem, Balanced-Plateau problem, and it is hard problem to solve. So actually, the complexity we face is coming out in the optimization in the classical data. So that's some problem. There, of course, are other approaches. It's a kernel method was also can be seen in classical, and it's sort of extended to quantum world. And in the classical system, this Dagger's, the inverse operation, is not so difficult to do. But in a quantum system, it is not that easy to implement Dagger operation. So that is a bit of problem when we move to a quantum regime. And there are some examples try to solve this quite simple isotropic problem, which is in a linear system in one dimension. So this is a nonlinear problem. So if you map in one dimension, you cannot have linear sort of solution because you cut somewhere, you cannot really distinguish blue to red. So you need to map into 2D, and then now linear line can sort of separate from blue to red. So in this way, we can have, if you go higher dimensional problem, then you can map that nonlinear problem to a linear problem. Then that's applied to the quantum, but you can see there's a little bit of, some part is successful, but sometimes still struggling. But the problem is, solving this problem is rather easy in the classical system because our computer technology is very much matured. So it's not so difficult for the classical computer to do this, but it's a quantum computer still in the simulation, still struggling to do this. So that is a bit of problem with NISQ processors at the moment. So another direction is probably thinking about more neural network type of version of quantum computers, and quantum neural networks has been considered. And there are two types of quantum neural networks. One is we think about qubits as a node, and connection, which is some gate you can apply, or some interaction in between them, is the edge of the network. So that actually the physical structure of qubits as a system is sort of forming some kind of network. That's why we can think that this is a quantum neural network. On the other hand, there are other systems, which is whatever the system we have, so take a NISQ processors and run some gates. And after that, on the Hilbert space, we have some kind of network is appearing in a unitary operator. So unitary operator itself can be considered as network, and that is kind of resource we can use. So that there are different type of networks, and that the neural network actually started to quantize perceptron. Perceptron is, as I put in here, it is very simple. This is a single perceptron. It's a classical model, and so mimicking neuron function. So input coming in, then we have output. So this is a nonlinear. As a nature of perceptron, it is nonlinear. And initial stage, people try to quantize this perceptron and had a problem, because if we sort of use unitary operator in here, unitary is, as we know, a linear function. So it's this one is nonlinear, it has to be a nonlinear function. So what we will do with this? So that was our initial problem. And there are lots of ideas to, for example, introduce noise effect or decoherence. This perceive some process to make the linear unitary operator non-unitary, therefore it will be nonlinear. But I'm not going into this. We are more talking about the unitary process, and this is more like a quantum computer. So, so here is a different emphasis. I have talked about that this quantum qubits network, and we have sort of seen that examples that people proposed to implement algorithm using this kind of thing. So if we have the network, then we can sort of design gate operation using this kind of network. So this, how we actually get gate operation out of quantum network is not that trivial. So the people designed how we do this, then it's how we get universal gate set, and so on and so on. So once we have this unitary gate set, then it is rather simple. Of course, computation is not simple, but conceptually it's simple to figure out how we implement an algorithm. So non-trivial part is appearing here. Then another way is thinking about that sort of network is created by the processor only. Hardware is sort of network is living in. So living in it's a Hilbert space, so we don't really see it. We don't really measure the network directly, but use that to perform some task. So it is easy to say, okay, quantum dynamics is a unitary operation, and if we can write unitary operation as a network, then we have a network kind of for free by that particular quantum system, time evolution. But then how we use that to solve a task? So this process is not really trivial. So we have to figure it out how we actually use that kind of natural process to solve a task, a computation task. So we talked about more about this today. So here is a different approaches to reduce the optimization cost, and one is these are both classical. At the moment, we are looking at classical system, and one is famous one is a reservoir computing. Probably people know about it in here. So we take some chaotic system or age of chaos kind of behavior in a complex system, and we don't quite know exactly what it is doing, but use this physical system and put input and output. Then usually it's a reservoir computing is used for temporal data. So you measure this and you put feedback in, and you optimize to complete the learning. And here is another way to minimize the layers. So it's not like deep learning. Deep learning, you have many layers, but we have very simple but huge network in the middle, and that's extreme learning machine. And the good thing is usually take the sort of Gaussian network in there, so we don't really optimize that what the network we want to initially just put it in there. And then, but if it's large enough, then it can be used to solve problem for static data. This one is not temporal. This is usually static data. So these two approaches in mind, we sort of review what we did for quantum circuit learning. And we have usually a hidden layer here is quantum processors or quantum network or whatever like this we have. And usually we try to sort of there are the parameters in here and try to optimize these parameters to changing the quantum networks. And that optimization is difficult. So what about we sort of separate quantum part and classical part? So now quantum part is only providing a large space in the Hilbert space, because that is what the quantum is good about. And here is optimization difficult. So the optimization is run by the classical. So it's kind of the merged with the quantum and classical together, and then see if this kind of mixed approach would work. So in some sense, we do not going to optimize this quantum network. That means it looks like a reservoir. Reservoir means not reservoir as a heat bath. I'm talking about a reservoir, computation reservoir. So it is providing a pure time evolution, but we do not control it so precisely. We have some quantum system and certain length of the time. It's just evolve in time. And because usually quantum dynamics is complex, so if we prepare the complex in a system, it will generate a huge complex network in the on the Hilbert space. So that is an expectation. Of course, we have to see that it's really true or not, but that is expectation. And then after that, we measure it out and take that sort of some information about the network, because we cannot get all the information, so some information at the end, and then optimize that classical only one layer network here, and to see if we can do this. And I think this is very simple, because we just put quantum and in front, and then measure it, and then only one layer classical learning part. So that is, as a system, is very simple. So as I said, this is so our design of new sort of quantum classical combined neural network. And key point is we need to think about how we encode information, because we are still thinking about classical information to be encoded, and what kind of system is appropriate to have this quantum neural network part, and how we do optimization. Maybe this is simplest problem. And it's turned out we have to carefully think about how we encode the information, because that is, it's in learning process, that data and the system properties needs to match. Otherwise, you cannot get good performance. So we have to think of how we encode information. And but on the other hand, this, as I said, this quantum neural network part is problem independent. So if we know how we encode it, we don't need to change anything. We don't need to program. That's the quantum part. And we can just change that encoding strategy and use exactly the same quantum system to solve different tasks. So that is a good thing about this design. Okay, so now we wanted to see what is this part is doing a little bit more carefully. And to do this, we kind of developed previously the way we understand unitary dynamics as a network. So how we do this, we used a Floquet type of technique. So this is a periodical driven system that time we used. And then we have, so one time sort of step, we have unitary. And then we sort of evaluated what kind of unitary is sort of, that unitary is, then now unitary is actually, unfortunately, it's not real numbers. So it's usually I in it. So we cannot really easily to convert to network. So we just use effective Hamiltonian to create that particular unitary. So that's different from physical unitary, but given by that Floquet unitary operator. And we can see this is just a matrix representation of the effective Hamiltonian. Then we can sort of map this kind of structure to the network, because there are transitions, and transition is strong enough. So with using calculation condition, then we can say, oh, this state and this state have an edge. Or if it's too weak, then this state and this state do not have an edge in between. So then we can sort of map that matrix, like adjacent matrix, into two network shape. So then we can see the different dynamics will have a different network, so the property will change. And applying this to a time crystal, and the time crystal, as you know, it is actually Floquet system, and you have periodic sort of control in there. And if it's forming, this one is used in first experiments back in 2017. But if this is perfect time crystal, then when you map that to the network representation, we only have these kind of diamonds. So that's really understandable, because doing a time crystal, this starting from this state and this state, it's a sort of going back and forth. So, you don't have any other connections. So they're all sort of diamonds. But then we are a little bit playful and started to change this epsilon to be a little bit, so start to melt the sort of time crystal. If we change epsilon, then it should start to melt, and see how it goes. So here, it doesn't move. Sorry, it should move to to form some. That's sorry about this, but it should be a movie to show to how we actually, when we change epsilon, how that network will change from a diamond structure for the perfect time crystal. Okay, so okay, so on the way to completely it's a random network, we have seen this kind of scale-free network because there is some kind of preferential attachment between states. So some part of the states wants to melt faster than other parts. So some part is not stable as other parts, is say. So in this case, we can see the preferential attachment in the network. That means we have scale-free network. And we just assumed this kind of structure usually used for neurons and things like this, memories and things like this. So we might be this kind of network can be used to quantum reservoir. So let's see if we can actually get anything good about this kind of network to make that sort of network to solve a problem. So this is our model. Then we first example is used MNIST image. It doesn't matter whatever it is. We will show some other examples as well. But there's some classical data, and the particular problem of this image is really large. So we have to think about some strategy to put that data into the physics layer, which is the input layer. And we have this kind of melted time crystal time evolution. Then after that, we measure all the qubits on the computational basis. So we have, if it's 10 qubits to the 10 nodes that we have, and we accumulate the data to have the distribution in the amplitude. So we will lose phase information. We only measure the computational basis and get distribution on the amplitude distribution. That is our output from the quantum hidden layer, and then we put that into one layer classical neural network to be optimized. So that is our system or our model of this algorithm or computational model. And the first example is this. Again, isotropic Gaussian samples, and we want to distinguish blue points from red points. And this first, if there is no time evolution, so t and t is 0, then we can not do anything. So that is the best guess we can have. And there are, of course, lots of errors because blue part has lots of red dots. And I'm not quite sure if it works again. Yeah, then if time goes longer, we can see. So this sort of time, each step is going to be sort of quantum part is longer and longer. Time evolution time gets longer and longer. So if the time evolution is too short, then we cannot produce enough complexity. So that's a reason we cannot do well. But if we wait long enough, then that sort of dynamics is complex enough now. So unitary is already complex, so we can solve the problem. So that is what it is doing. So we need to wait a certain time. That is a computational time. It makes sense because it shouldn't solve instantly. So this is a simple problem, of course. So we should try this MNIST problem. Unfortunately, the MNIST handwritten number data set has so each image is 28 times 28 pixels. And that is really huge compared to we are using only 12 or 13 qubits. So this is really big compared to the number of qubits. And each point is grayscale, so it has eight bits in each pixel. So actually total size to accommodate that is quite big. So we have to, we run PCA map. That means, you can have some kind of principal value for the data and extract the important information out of this. And this one is not very heavy to run. And after doing this, we used only 2n data from the most significant first. And we can put that into this input layer. And so this is how we did. So actually, yes, 784 components, but then we only take 2n principal components to input. How we input is we have two continuous variables in each qubit, of course, with a certain precision, but we have theta and phi. And we used both. That is very important. You cannot use only one. It seems it's more efficient to use both theta and phi to encode. So that's why we have not only n, we have 2n because of this factor of 2 coming out of here. And we put in a Prof sphere for each qubit. So actually encoding is not complicated. It's only just a single qubit rotation we need to apply. And after that, we just do the melted time crystal time evolution, then see what we can do. So here, what we can do, this is sort of performance of testing accuracy. I didn't put in here is learning curve, so because it's going to almost 1, so I wouldn't put it in, but so this is the testing accuracy that which is below, that's learning one. But anyway, so starting from error 0, which is time crystal, so not doing anything, and that is already here, but then if we turn that epsilon on, that means we started melt, and the dynamics is more complex, and somehow we max it out around here, it's coming back. So it's interesting because, this is kind of transition from this point is some kind of transition from scale-free network to random network. So here is a network property will change that we know from the previous research result. And of course, it's this kind of network property. The network need to be really large to say, there's clear transition in there. Then we have only 13 qubits. That means the transition is not that clear, but we can still see around here, this region. It's sort of network started change from scale-free to more random. And that is where sort of we are getting that sort of maximum accuracy when we have scale-free network. We are not saying this is the general or universal measure. Only we are saying in this case we can see this coincidence, and to say this really works, we need to have more research on this. But on the other hand, it's sort of looking at this performance. In this case, we only use 11 qubits, and it achieved 97% accuracy. And if you look at tensor operator approach, for example, we needed 784 qubits, and drastically sort of reduced. Not really, we're not saying 99%, but still, only 11 qubit could achieve this kind of fidelity is something we haven't seen before. And I think this is very interesting approach, because then we use some kind of natural system which is only 10 to 12 qubits, maybe it's a 10 to 15 qubits, a small number of qubits relative to 50 qubits processors, and still we can sort of make them working for computation. Okay, so next one. So this one is says showing a training accuracy, and now training accuracy, you can see that it's going to be 100%. That means that it's saturated. In this sense, we have overfitting problem. So that is something we always have in classical and the quantum case is not an exception. Then we still have overfitting, but then we found the simple dropouts technique will actually work quite well. And that is very interesting, because usually dropout is not that easy thing to do in a classical case. But in here, we have only one layer, and the dropout is quite easy to apply. So then we can see that improvement using dropout technique. That is sort of, just nice to see. So classical techniques is easy to apply because this structure is so simple and have only one layer. So that's a reason we can apply still lots of different techniques as developed in the classical world. Okay, so I think I'm really pushing the time maybe, so I just move on to the briefly another topic, which is neural sensing. So this is an experiment done in China, and I just briefly mentioned. So we are talking about up to here with classical information, and we're saying how to input classical information is important. But sooner or later, we will have quantum input. For example, we may like to combine quantum neural network with quantum sensors, because quantum sensors should give quantum state, or quantum simulator should give the state. But the measurement we can apply is very limited. So, in experiments we cannot really, the theorists can design whatever POV of measurement, but it's very difficult to implement such a thing. So instead of developing each difficult measurement, we can put quantum computer before the measurement, so that the measurement can extract more information. So that is what we're trying to do. So here, the system is producing as a quantum simulated a certain state, which is localized or algorithmic states in this case. And after that, we have the quantum classical neural network is optimizing to see if the state is either algorithmic or localized, because we don't really not specifying. No, we're not doing tomographic approach. We only want to say that statistical property of that state. So we just only measuring one qubit, because that is binary information. Then actually this approach can work. In the experiment, we have seen improvement of the measurement using this kind of network, and that's quite promising, I think, to think about development of quantum sensors, for example. Yeah, so I just skip this, and this is the result. So, as you can see, we can. So we have different size, 4x4 to 8x8, and we can see that sort of this binary information, algorithmic or localized, it will be separated in here, so we can measure it and we can tell which one we got. And we don't know exactly what kind of state we have. We only know it is algorithmic or localized, for example. And that kind of thing in the future can be applied to a phase transition. So we can probably measure more about phase transition and more predict precisely from this kind of simulation in the future, I think. So here is a summary, and we have seen the different type of different ways to use this kind of technology. Is not just only NISQ processors, but NISQ technologies. We are producing technology to actually create NISQ processors, but not only NISQ processors, we can use that technology for other things, and we can probably learn more about quantum science out of it, as well as developing new type of technologies. So here we are now, and I will summarize this, and thank you very much for listening. And we have open positions at OIST, so if you're interested, please let me know. Okay, thank you very much.
Thank you very much, Nemoto Sensei, for very interesting talk and introducing us to the concept of neural network and bring it to quantum processor. And actually, we can study various things like Floquet states and time crystal. So we have time for questions and comment. We can accept several. Please, yeah, you can raise your hands and grab the mic and turn on your camera. Any questions? Yeah, yes. So from Dr. Yanuar Sarwono, please.
Thank you, Professor Nemoto, for a very nice talk about NISQ processors. So I have a question, Professor Nemoto. When you in the quantum neural network slides, what is the time? I mean, when you present the quantum neural network slides, what is the time scale when we represent the dynamics of when we represent the dynamics into the network? Is it quick, or is it computationally costly? Yeah, thank you.
That's a very good question. When we used the model of time crystal, and we can finish that sort of time evolution well within the coherence time of the experiments in 2014 ion trap. So I think we believe we can, with the current technology, particularly with ion trap, we can do this within it's less than half or something like this of the coherence time. So I think we will have enough coherence left in the system. And recently, I think relatively recently, using Google chip, they demonstrated time crystal on the gate basis. So this kind of thing also promising. I think we can probably use that kind of gate system. But I have to say, if you to decompose the gates, then you have usually need more time, because the gate evolution is not really efficient in the sense. We need a gate because if you move into a fault-tolerant quantum computer, or even just move to a logical qubit with using error correction code, we have to deal with gates. We have to work with gates. We cannot apply a certain arbitrary gate anymore. Single qubit operation is not possible to do with arbitrary angle. Logical qubit structure is restrict us to use certain gate set. But at the moment, we are only working with physical qubit, and we can sort of, continuously control it. And usually that is much shorter in the execution time. So I would say in that case, ion trap type of structure is working well. But recently we found we don't need to go into the Floquet system as well. We can have other system to do. So I think Floquet system is tend to have more time in the time evolution because we have time steps. But I think we can shorter even at the time. So I mean, the feasibility is quite high in that sense.
Thank you much for the response, Professor Nemoto. Thank you, Professor Dr. Hamzah Fauzi.
Thank you very much. I think it will be also interesting to study quantum phase transitions using this neural network concept stuff. Right. Any other questions we have? We can accept 2 long questions and several short questions. Any, please. Yeah, Dr. Ahmad Ridwan, please.
Yes, thank you very much, Professor Nemoto, for a very wonderful presentation. I just heard the news last year that a team based at the Delft University of Technology reported that they built a Floquet time crystal not in a quantum processor, but using nuclear spins of carbon atoms in a diamond. And yeah, recently there are some news that many papers are retracted from the similar groups. So could you comment on this finding?
I don't know if I'm following up that particular research recently once, but the time crystal, of course, has been sort of investigated in many different systems. And superconducting is only one, diamond-based. And there's another one some time ago, probably that one is 2 years ago or something. So there are lots of results coming out. And I would say all these candidates for this kind of technology. And, there are some others actually not considered well enough. So I think, more possibilities and, that kind of technology, the most important thing I would say is, that kind of development, we don't really need huge, not necessarily big fridge, that don't necessarily this huge amount of money we need to develop. My much smaller system can be some use for the quantum technology. I don't know if I answered your question, but
yeah. Thank you very much for the answer.
Right, so there's another one from Dr. Khairul Anwar from Telkom University, please.
Yeah, okay. Thank you very much, Dr. Hamzah, for the time. Professor Nemoto, so first I would like to thank for the very nice presentations. Actually, I have one question. You saw in your slide about the quantum machine learning where you are using the Hamiltonian encoding. So would you please give comment according to your experience, which is better, or maybe pros and cons between the Hamiltonian encoding and compared to the amplitude encoding?
Compared to?
Amplitude encoding.
Amplitude?
Yes.
I'm not quite sure I'm answering that. I'm understanding the question properly, but we don't think about any difference between, in this case, Hamiltonian encoding or unitary encoding, so unitary operator encoding. So it's just kind of mapping. So that means we can still use work with unitary. That means a gate sequence, or we can have a Hamiltonian to generate that what we want naturally. There is no difference in the theory, but only the implementation. So which is easier for us to do, and which is we can keep more coherence. So if you have unitary-based or operator-based system, and of course we can work with that. And if you have some Hamiltonian, like in Ising model or whatever like this, you have some certain Hamiltonian for the more working with annealing type of thing, and you have Hamiltonian there, and then we can sort of turn that into this model. That's one way of doing things as well.
Okay, thank you very much, Prof. Nemoto.
Thank you. Perhaps last questions coming from the chat box from Dr. Muhandis. Questions. As a theorist, do you think NISQ can produce something practically useful in the real world? As they
okay, well, I was a little bit pessimistic about it because, the depth, computational depth wasn't enough. Theoretically, it wasn't enough at the beginning. But now I think, a little bit more optimistic, because then this kind of approach, we really don't need to run the gate sequence. So then say, we can see the time evolution of the natural system is pure enough now and to do something. And okay, you might say, we are not solving difficult problem. That's true. We can do that in a classical computer as well, because it's just only recognizing these numbers, or we can do a bit more complex things. But think about, how much system we need to do that classically, and we can sort of have very, very small system. For example, if we have 50 qubits, we have 10 to the 15 nodes network. That nodes size is the same as human brain synapse, the number of synapses. So if you think about it, we can sort of compactify that's learning system quite dramatically using quantum system. So it's very difficult to say how quickly we can solve the one problem, because this machine learning thing it's not designed like this. And I can say the learning process is faster than classical in this case, because the learning is only one layer. So it's thinking about deep learning, it's much more time you need. And here is much shorter. But at the same time, we have to repeat it, because we have to accumulate the amplitude distribution information in the sense. So the total time to do this, that also dependent on the hardware as well. So it's very difficult to evaluate like this. But think about 10 qubits. 10 qubits can be very, very small device and can put it anywhere almost, if we can sort of control it in a normal temperature. And that kind of thing is, give us new applications. That's what I think.
Right. Thank you very much for the wonderful answers and questions and comments. Thank you very much. Unfortunately, time is up. Thank you very much, Nemoto Sensei.
Thank you very much. Thanks for listening.
Very nice talk. Thank you.
Thank you.
Much.
Bye.
Bye.